All right. Good morning, everybody. Welcome to Project Sauron's final design review.
Well, I've got 11 o'clock sharp here. I'd like to welcome folks who are joining us online, those of you here in person. It's my pleasure today to introduce our team OD Laser. They're going to be talking to us a little bit about their approach for orbital debris mitigation. In addition to just doing some top-notch engineering work, OD Laser's got a really great team dynamic. They've been a big pleasure to work with. I really enjoyed it, and I'll turn it over to Ethan.
All right, we are Team OD Laser. I'm Ethan. Here we have Oli, Cody, Alfonso, Ryan, Anna, and Brendan. We had Doug. He is an exchange student, so he isn't able to be here today, but he worked on this in preliminary design. So I will hand it off to Oli to get us started.
Okay, so just a brief roadmap of what we're going to be going over today. We're going to just start with a basic introduction. I'm going to talk about the concept of operations for our overall system. Then we're going to get into our subsystems and really break down all the tests that we've completed and talk about any confirmation and the requirements of each of those. And then we're going to talk about how the system integrates as a whole and configuration management, and then a brief conclusion as well as a demonstration at the end. So this is our concept of operations. Essentially, our project is an orbital debris laser that would be on board an orbiting satellite. So it would launch, deploy into orbit, and then it would find a target using ground stations and shoot it with a powerful laser ablating material, causing it to deorbit. So again, this is our team. As we introduced, I'll just give you some information on what we've all done. So Ethan Carlson is our project manager. He's also done our sensors. I'm the assistant project manager, and then down the line, Alfonso does software, Brendan does power, Cody does laser, Anna does supporting assets, and Ryan does attitude control. So a little bit of our history. We had prelim last semester, and that's where we got a lot of our design done. And then we came back from break and we did our critical design review. We had a little bit of change during that because we realized that our infrared sensor we had already purchased did not have sufficient resolution. So we implemented a visual sensing scheme for hit verification, kept the IR for target definition. Then we started our configuration management, and then we've been doing testing ever since. And finally today we are at the system verification review. So a little bit of our subsystems. I'm not going to go too far into these because they will be further defined as we go through this PowerPoint. But each of our 6 subsystems is defined by its components and responsible for individual things. So Cody is going to talk about our subsystems and then get into the laser.
Hi everyone, I'm Cody. I'm going to talk about the overview of the subsystems first. So what we're going to do here is start on the right side of this slide with the target, and we're going to follow the information. So you can see in the blue arrows, the visual sensor and the infrared sensor takes their respective information from the target and passes that to the software. At that time, the software runs through the algorithm. It's going to determine what direction the motors need to move in order to center our target on our screen. Once it determines it's centered, it's going to turn on the laser diode. At that point, the visual sensor is going to check to see if that hit was successful or not. If it was, the program stops there. Now I'll go into the laser subsystem. So these are the requirements for the laser subsystem. We'll get into the details of these on their respective tests. This is the laser diode itself. So it's very small. It's on the left or right-hand side of the system here. It's only about 12 millimeters or 7 millimeters in diameter, and it's just powered with a 5-volt DC voltage. So the first test we did is the laser operations test, and this covered requirements 5.0, 5.2, 5.4, and 3.6. This mainly focused on the ability to power the laser with our software, with our Raspberry Pi, and verified the ability for the laser to actually adequately power for a long enough time that we can verify our tests. So as requirement 5.0 was the output wavelength of the laser. So we chose this green laser, and because it's basically the most easily visible color to visual sensors, and so it'd be the easiest to actually verify the hit with. This failed because we didn't have a specific way to test for that 520 to 530 nanometer wavelength range. However, we do believe through analysis that the laser falls in those wavelength ranges, and it is very bright green, so it worked for our test. The output time, it could output for more than 30 seconds. It is able to be controlled by the Raspberry Pi, and the software can turn it on and off when it desires. 5.3 was just the mass test for this laser. It's very light, so it was able to be supported by our structure. And it was met. So these are all of the tests basically there. So the only one that failed was the wavelength range, and analysis tells us that it actually passed. So now I'll pass it off to Ethan. Oh, actually, so this is the subsystem integration. So you can see the laser in the middle there, basically. So it receives power from the power subsystem, and it is controlled by the Raspberry Pi. It is mounted to the attitude control system here, so it can turn with the sensors. Now I'll pass it off to Ethan. For the sensor subsystem.
All right, so I'll be talking about the sensor subsystem. Again, we're not going to go through all of these requirements as they're defined later. So to begin the system definition, we decided to add this visual camera as the IR camera was not sufficient, as we spoke about earlier. We went with the T3 Pro, which is a phone attachment camera, and the HQ sensor with a 35mm lens, which attaches directly to the Raspberry Pi. So in the IR sensors visual test, we went over requirements 1.0, 1.1, and 2.1. This is basically just being able to see something through the IR camera, have adequate resolution, and then get that image back to the software. So here we see that all of those are met. The IR resolution was met through 240 by 240 to 400 by 400 resolution, and we could get that image back to the software. So the next test does basically the same thing as the IR, but now with the visual camera, with the addition of a zoom capability. So we wanted to be able to see the image through the camera, be able to zoom at a distance that we decided was 70%, and then also have that image come back to the Raspberry Pi. So here all those tests were met. We were able to zoom to any desired percentage, and here we chose 70, and later we will show you in our demonstration we changed that to 20 because of edges. And here we have the IR sensors thermal test. This is basically telling you that the IR's sensor's ability to see temperature. So the basic idea here was that there was 50 millikelvins to 70 millikelvins of fidelity. And here we decided to try and find the difference between 1 Kelvin, just because we don't have the equipment to be able to go that precise. And we see on the next slide that that was met. We were able to tell a difference between two objects that were 1 Kelvin apart in degrees. So here we show that the analysis and all the tests were met. Through analysis, we basically showed through specifications that everything was met, and then the test, as well as I said earlier, showed that those were met. And through the integration, we see that there is data coming back to us from the supporting assets, as the supporting assets is that target. So we're getting that visual data back to the camera. It is also sitting on a tripod, so it's mechanically attached to that. We are getting the attitude control to mechanically move us, and the software subsystem, we are giving data, and it is giving data back to us. So I will pass it off to Alfonso for the software subsystem.
These are the requirements for the software subsystem. We'll go over them more in detail in the next slides. So for subsystem definition, what the software is going to do is first it's going to calibrate the IR sensor so that that's the only white thing in the frame. Then we're going to send commands to the attitude control subsystem so that the target is in the center of the frame. Then we're going to turn the laser on, and then we're going to verify if the laser hit the target, and then we're going to turn the laser off. And that's the end of the software part. Then the language that we used was Python, and we used the Raspberry Pi, and the main library was OpenCV. For our first test, we had the denoising test, which is just to verify that the software can denoise the images. The requirements that we tested were 3.3, which was that the software shall denoise the obtained images, and then 3.4, that the software can determine an IR difference between the debris and the backdrop, and both of these requirements were met. Then we have the software centering test. We tested requirements 3.5 and 4.0. The test was to verify if the software and the additive control subsystem can center the target in the frame. 3.5, which is that the software can send commands to the additive control system and determine when the target is centered in the frame, was met. And 4.0, which is that the pan and tilt module can change direction so that we have the target in the center, was met also. The last test is the software hit verification test. This test only tests requirement 3.7. Our test is to verify that the software can determine where the laser is and where the target is. And using these two information, we can know if the laser hit or did not hit the target. So there's the three cases that we had where the target is in the frame, but the laser was not detected, and the software was able to determine the edges of the whole target. Then the laser was detected, but the laser was not in the frame. You can see that the software knows where the laser is it has a black dot right in the laser. And then we have that the laser was detected and the laser hit the target. And requirement 3.7, which is that we have to verify a hit with the laser, was met. So all of our requirements were met analytically and experimentally. For our system integration, the sensor subsystem sends the software information, and we send information to the sensor. We also send a 3.3 volt signal to the power subsystem, and we send commands to the additive control subsystem, and we are mounted on the supporting system, on the supporting asset, so on the mount. And we send a 3.3 volt signal to the laser subsystem. And now Ryan will talk more about the additive control subsystem.
All right, so here are our requirements for the attitude control subsystem. We're going to go over them more specifically in their tests. So the attitude control subsystem is what points our sensors and our laser. It is comprised of this bracket setup and these motors right here. So our first requirement was a pointing accuracy test, which was 4.1, and we tested that by shooting the laser at a wall that was 20 meters away and moving the smallest we possibly could. And in the next slide, we can see that we met it by being under 0.1375 degrees. We were actually at 0.04 degrees. Our next test was the operation time test, which is a bit of a misnomer because it also is the range of motion and stability tests. So what this test was we gave a random coordinate to the ACS and told it to point at it. Then we just had it move randomly for 5 minutes. So in the next slide, we can see that we hit all of those. We were able to point at our random location. We operated for 5 minutes. This was all commanded by the Pi, and the tripod didn't fall over. So we hit all of our requirements there. And our next test was very simple, just if this could carry 1 kilo, so we put a kilo on it, and it didn't break, as you can see. Our final one was for calibration. So all of these sensors are mounted side to side from each other, so they all need to point at the same point at 20 meters away. So what we did here was we adjusted these so they were all centered to the same point and measured the difference between where we wanted them pointing at and where they actually were. And if that was under 3 centimeters, we passed, which we did. So here you can see that we met all of our requirements in test. We could not confirm 2 of them through analysis, which was the range of motion, because until we built it, we were unsure the limits of our cables, and the calibration, because until we built it, we were unsure how good we would be with our hands at aiming in together. So here's our integration. And as you can see, attitude control, it is held up by the supporting assets, and it moves the laser and sensor subsystem, powered by the power and commanded by the software. All right, now I'm going to hand it off to Anna for supporting assets.
Hello, I'm Anna, and these are the requirements for the supporting assets subsystem. I will be discussing it later in the slides. So for the design, we can see that we have two tripods. The first tripod is a targeting tripod. It holds the laser, the sensors, and the software. And then on the second tripod, we can see that it holds a target, which is a 20 centimeter by 20 centimeter piece of aluminum. For the first test, which is a targeting tripod height inspection, this one relates to requirement 6.1, which states that the target shall be of height 1, should be able to be adjusted to a height of 1.5 meters in order to easy manipulation of the components. We tested this just by setting up the tripod and measuring with a measuring tape if it was 1.5 meters. And we can see here in the verification table that this requirement was met. For the next test, it is a targeting tripod mass inspection, which relates to requirement 6.2. This one states that the targeting tripod should be able to hold 3 kilograms of payload, which, as I mentioned earlier, is the power, the sensors, the laser. And we just tested this by setting up the tripod and making sure that the tripod was stable, it didn't tip over or it didn't break. And we can see in this table that this test passed. The next test was the backdrop material inspection, which relates to requirement 6.3. This requirement states that the target shall be in a backdrop that is easily differentiable from the target. So in other words, just using a dark backdrop in order to detect the edges of the target with the visual camera. And we tested this by using most of the time we just used a backdrop. And we were able to confirm that this test passed by detecting the edges of the target with the software and the visual camera. For the next test, we have the target material inspection, which relates to requirement 6.7. This requirement states that the target shall be made of either aluminum, carbon fiber, or titanium in order to resemble what space debris is made of. This test was very simple. We just set up the tripod and confirmed that, in fact, the target was made of aluminum. For the next test, we have the backdrop and target reflectivity test. This test related to requirements 6.4 and 6.8, which state that the backdrop should not reflect the laser when we point at it, when we point at the backdrop, and it should reflect the laser when we are pointing it to the target. We were able to test this by setting up all of this, the targeting tripod, and then setting up the laser to first hit at the backdrop and then hit at the target. And then if this laser spot was visible in the target, the test passed. And if it was not visible in the backdrop, the test passed as well. But as we can see in the verification test, the backdrop reflectivity test failed because we were able to see the laser spot in the backdrop. However, this was fixed by just fixing the software and configuring it so that when we saw the spot in the backdrop instead of the target, we were able to tell that it was in the backdrop instead of the target. By detecting the edges of the target in combination with detecting the laser. But the target reflectivity passed. And then lastly, we can see here the supporting assets integration. We can see that it has a mechanical connection to all of the subsystems, the laser, the software, sensor, and attitude control, because it holds everything in the targeting tripod. We can see here in the confirmation table that all of the requirements passed by analysis, but the only requirement that failed, like as it was mentioned earlier, was the backdrop reflectivity test. But this did not make a difference in the project because we were able to fix it. Now Brendan is going to talk about the power subsystem.
All right, my name is Brendan, and I'll be going over the power subsystem, otherwise known as Black Magic. So these are the requirements. I'll get into those a little bit later. So these are the end components that we used in the power subsystem. These two on the left, they are the PCBs that we soldered up. They involve the stepping down of the voltage to 5 volts so that we control the motor signaling. Sorry. And then also level shifters so we control the motor signaling and lasers. And we also used a 24 volts power supply. And we also included a powering for the Raspberry Pi. Next slide. So these are the lasers, the schematics for the power subsystem. As you can see on the right side, we have the level shifters and a 5-volt regulator. And those level shifters, they control the drivers for the motors. And the 5-volt regulator controls the source for those level shifters. And over on the left, you can see the laser control schematic. And the laser control schematic involves another 5-volt regulator and a MOSFET in order to control the turning on and off of the laser from the Raspberry Pi. Next slide. So here's our power subsystem budget. We have about 23.8 watts. That's what we expected. And we met this pretty well. Next slide. So we had one power subsystem test, and that was testing the voltage from 2 different places. So the 24 volt power supply gave us 24 volts, and we met that pretty well. And we also had 5 volts from those 5-volt regulators. We did not end up having a test for the power supply, 23.8 watts. And we met this since we got the system to work well under the all of the other tests, right? So that power supply was about 200 watts, and we only used maybe 20, right? Next slide. So again, we met all of our analysis. We met all of our tests based on choosing the right components and then testing on later. Now, to get into a little bit more overview of the integration, we have 3.3 volts signals coming from the software of the Raspberry Pi, and that is being turned into usable data for the laser and attitude control. And we also are sending 24 volts to the motors themselves and 5 volts to the signals for the motors. Next slide. All right, and now I will pass it on to Ryan for the integration.
So here are our system level design requirements. So starting off, infrared has to be able to display the target at 20 meters. The IR sensor needs to be able to have sufficient resolution to tell the difference between the target and the background. We put that at 50 millikelvin to 70 millikelvin there, but we couldn't test that. Software needs to be able to recognize the target and output controls to aim at the center. We need to be able to aim at the center using the pan and tilt. The laser output needs to be within 520 and 530 nanometers. We need to have a stable environment. We need to be able to do all of our whole demonstration within 5 minutes. The electrical power system needs to provide enough power. We need to have sufficient resolution from the visual to verify our laser. And this all needs to cost less than $2,500. So here are our design metrics by subsystem. So as you can see, the sensor, software, attitude control, and power subsystems met all of their design requirements. The laser subsystem did not, because as we mentioned earlier, it did not get the wavelength we wanted. And the supporting asset subsystem failed because the backdrop material was reflective and we didn't want it to be. Here is that again, but with our primary requirements that I just read out. As you can see, our only failure on these was for the laser output frequency. So here's our full system integration. At the core of it, we have the attitude control subsystem, which aims the laser and the sensor at the target, which gets a signal from the laser, which then goes to the sensor to tell the software if we hit or not. The target also has an IR signature that goes to the sensor to tell the software where it is, and the power subsystem powers everything. So here are where we had some discrepancies in our analysis and our tests. So our first one there was our infrared camera's range by its resolution. We expected that it would be sufficient, and we would have about 9 pixels of target in our viewfinder, and we were wrong. We had 25 pixels. So what that probably means was this has a narrower field of view than what we calculated previously. So that's actually a good thing. The ACS precision, this should have been about 10 times more accurate than it needed to be. Turns out it was only about twice as accurate as it needed to be. Still not a problem, but that was likely because of our control scheme not allowing us to do perfect individual steps on the stepper motors. Our laser frequency was, as we said earlier, outside of our bound. That was unfortunate, but we were able to fix that effectively by making our software smarter and adjusting our numbers that we were looking for. Background reflectivity, we wanted it not to reflect, it did. So as a result of that, we had to make our software a lot smarter and be able to see the edges of the target and tell when it was inside and outside of the target. So basically the first 2 were good or not a problem. The bottom 2 we solved by making the software smarter. All right, and now I'm gonna pass it off to Oli for our configuration management.
Thank you, Ryan. So this is an example of our configuration management tree. It's just one branch of the tree that I'm going to take you through today, but we're going to go from final assembly to targeting tripod to the ACS subsystem and then to the IR camera case. I'll show you these as we go along. So if you start in our bill of materials, you can see our final assembly is family 66, instance 1. From there, the targeting tripod is within that assembly, and that's family 200 for our sub-assemblies, 3,000 for the instance. And then on top of the targeting tripod, we have another sub-assembly, that's our ACS. So again, it's 200 family, but instance 4,000. And then the camera case is within that sub-assembly, and that is 76, which is our manufactured parts. And the drawing for that is there. That's kind of an example of what our individual parts look like in our configuration management. So as you can see, it has the part number and as well as a couple of other details. We manufactured this in the RPL here at Embry-Riddle, and it's made out of PLA plastic. So our release documents, the status of those are CM was officially released on 4/26. It's numbered 0, that's its first iteration. And in the ECO, the numbering scheme is going to start at 0 and go to 1 and so on and so forth. I'm also going to talk a little bit about the budget while I'm up here. So we have a mass, cost, and power budget. The mass of the total system is 1465 kilograms, which that, if you don't count the tripods, because those don't really matter in terms of what's going to be a payload on a satellite, but the payload of the targeting tripod ended up being about 3 kilograms. And then the cost, so we were given $1,000 from the COE. We were awarded $1,500 from the URI. And we used 1,142 of those dollars on the sensors. Our IR sensor, which is this tiny one right here, was $900 something. And then that didn't work very well, so we had to spend another $200 on a second sensor. And from there, everything else fell into place, but we ended up having a reserve of about 630, so we didn't do too bad. And then power, of course, like Brendan talked about earlier, 24 volts, or watts. And then Ethan's going to get into the demonstration.
All right, so I'm going to do a brief overview of our ConOps for our test bed. We've went over this a couple of times already, but the whole goal here is to get an IR signature from the target. The target will be somewhere in the frame. We will take that IR signature, center it. Then when it is centered, the software will switch to the visual camera. The laser will turn on. The visual camera will tell us if we've hit the target or not, and then the software will give us that command window telling us, yes, you've hit the target, or no, you haven't. So this is just an image we took from one of our tests. You can kind of see everything here. That little small box at the end is the target. We have the software attached to our targeting tripod that is on the right there. So going over the design metrics and requirements, some of these are reiterated. Basically, this is telling us everything needs to work with software and everything needs to be able to stay on this and work together. So that this is just a compatibility of the entire targeting tripod. And on the next slide, we have a continuation of that. So here we have a demonstration video. This is going to be very quick. So I have a slow motion one after this. I would advise you guys to focus on either the top left or the middle halfway through. I'll try to work you guys through it as it goes. You can just click the next one, like this quick slide. Okay, so here we're setting our thresholds. This is basically telling us where the white dot is and to make sure that the only thing in the frame is our target, which is that white dot. This is changed up on the left with the threshold and exposure value. After this, you're going to see the tripod on the top left, a centering box in the middle, and then our laser on the right, and the command window is still doing its job, telling you what's going on. So here we see it's centered. That was very quick. The next slide, you'll be able to focus a little bit on both of them. Here we see that the laser was turned on when that code said centered, and then we can see from that command window that the laser was detected and we did hit the target. So this is just a slower version of that, more focused on the actual movement of the target. So if you can look at the left, I guess your right and the center, that will be able to tell you what we're actually doing here. So this is a little bit better visual that you can see the targeting tripod is moving while that software is showing it's moving as well. And then this is gonna turn on the laser, and then it will tell you that it hit. So basic idea is the same thing as the last slide, just a little bit slower. So from this, we've learned a lot of lessons, as you can see here. We've followed effective teamwork. We've worked together on all of our documents in creating this very intricate targeting tripod. We gained a lot of knowledge on our subsystems. I know I didn't know too much about sensors, and now I know a lot more than I thought I ever would about sensors. We practiced delegating tasks and trusting each other with those tasks. And we considered all ideas feasible. No idea is ever too crazy, too out of this world. We were prepared to rework the project. As we said earlier, from preliminary to here, we had to add this visual camera. And we adapted very well for that unforeseen event. And we also have adapted to the fact that we couldn't test in our normal testing location due to the fire. So we were able to find a hallway instead of the gym to test and still get the results that we like. And iteration improved to keep this engineering process going, as we had to keep editing the code, editing the motors, trying to cool them down. And at the end, we ended up getting a full product, as you guys had just seen. So for acknowledgements, we'd like to thank Dr. Mangum and Dr. White for helping us through the class, through the process, through all of our documents and most of our hardware. We'd like to thank Grederson, or Dr. Grederson, for helping us with the laser, as he's the one that told us that it probably wouldn't work and we had to use that visual camera, and his ability to tell us that pretty early allowed us to adapt. We'd like to thank safety, as we didn't want to break anything or hurt anyone when we were using this. We'd like to thank Ginger and Dr. Ann Betcher, because they helped us with all of our finances and making sure we were within that budget. And we'd also like to thank ERAU facilities and the custodial staff for allowing us to test after hours. As we were using hallways, we did make sure there was no students in the way while we were testing. So we can either ask questions right now, or we can see a super cool video of our secondary objective, which is tracking me. So I would like to show it. Okay, perfect. So this is basically, we set it up basically this far apart, and it's going to have a laser tracking me as the heat signature. You'll see in the beginning it tracks very well, but since this was our secondary objective, we didn't really focus on it too much. So you'll see at the end the laser lags a little bit behind me. That just has to do with the iteration of the code and the motors and the power supply not working completely together. But if we play the video, you guys will see it. So we're doing the same process again here, making sure that my face is the only white thing. in the in the camera. And then on your left here, you'll see both of them working together. And hopefully you guys can see it. You'll be able to see the motor move up and down, left and right, depending on how I move. You'll see the laser turn on here. It's tracking my face. And here you'll see that little bit of lag because the centering isn't completely meant for this. But we're glad that we were able to actually track ourselves, or track anything for that matter. So we can go back to questions if you guys have any, and thank you guys for your time. Okay. It'll be the mic lady. Make sure it's on too. Ryan, you might want to just stand up here.
Are we on? Maybe? Okay. All right, first up, so did you guys look at test parameters in a space regime? And I'm thinking of things like time on target.
So not really,
Okay.
is the real thing. We wanted to not take an insanely long period of time, which is why we had the 5 minutes requirement on ourselves. But a lot of making this faster would be optimizing our software, getting really good and really fast motors, and that was outside of the scope of this class to our
Okay.
knowledge.
Yeah, I was just curious if you guys had thought about those specific details through the process, but again, finite time, there's only so much you can do. So if you guys were in a space regime, like I'm assuming this is supposed to operate, how would your sensors need to change? You guys said that you learned a lot about them, so I'm curious how far you took that.
Well, so what we would need to change most is we would want a more directional IR camera, because this one has like a 40-degree sweep, and we would want that to probably be more like 2 or 3 degrees, because we're aiming at a target that's kilometers away, and that would allow us to have a lot more resolution relative to the size of our target. And we would ideally probably not want to have a visual sensor at all on that scheme. The reason we had a visual sensor here is because we wanted to use an IR laser and detect it using the IR camera, and that would have been really nice, but our IR camera did not perform to the specs. It couldn't look low enough into the IR spectrum for the IR laser we had, and if we wanted to get an IR laser that could be seen by that, it would have costed like $2,000 and been hilariously dangerous for us to use. So we would probably want to have a more focused IR thing and a different laser that would be visible in it.
Okay, so you'd still use a single IR sensor for both detection and confirming that your laser made contact?
That's what I'm thinking of.
Oh, okay. Yeah, I just want to make sure I was following that. Okay. Yeah, I want to ask the follow-up then. So last question I have was, is your overall test setup subject to environmental conditions? And I ask this because I don't know how much research you guys did into like directed energy for military applications, but they're incredibly environmentally sensitive. So I don't know how far you looked into that.
We didn't look deep into it before our tests, but in our tests we saw it.
Okay.
Because it was very difficult to do this outside at all, because the shrubbery was too bright. When we did it inside, like there was a router in a hallway that was just bright as can be, and so in the test that we ended up doing and showing you now, we actually had a bunch of cardboard boxes that we put around routers and lights and things in order to clean up our environment.
So as a bit of a follow-up question then, did you guys invest any time, or did you even have time to do things like target recognition, identifying, things you should be looking at versus things you shouldn't be?
We didn't really have time to do that.
Okay, yeah, no worries. Because the application there, of course, would be you don't want to look at the sun and try to zap that, or the moon, and actually the Earth to a certain extent.
Yeah.
But no, it makes sense. It's an interesting challenge. It's really hard to use lasers in space, it turns out. So good work. I don't have any other questions.
I can follow follow up with a few. If folks from the audience, I ask these guys questions all the time, so if folks from the audience have questions, we want to prioritize those. I really want to, before I give you any questions, like, it's really pretty incredible what you guys were able to do. I mean, you implemented a real-life, honest-to-God machine vision application under active feedback control using an infrared camera in a couple of months. That's, I mean, borderline unbelievable. It's really awesome. I want to ask you to maybe tattle on yourselves just a little bit. You know, a big part of this course is following the product development plan, and requirements are kind of the cornerstone of beginning a project. I know, you know, there's an idea that you want to set your requirements, have those frozen and set in stone. Can you talk to me a little bit about some of the struggles that you've had with requirements, maybe wanting to change requirements like 3 days before the project's over, and those kinds of things?
Yeah, so we had a few requirements that we realized should have been made in the, or would benefit if we did it during our testing. For example, the one that I said from the sensor subsystem, we initially thought 70%. That's just based on some knowledge I looked up in research. But then when we did the actual test, we realized 20% was a lot better. And so it was a little bit difficult in that sense to be able to, I guess, estimate what we would want to use. We also didn't know if we would need a backdrop, and we ended up needing one because we weren't in the gym anymore. So there was just a few requirements that we would have liked to change. We would have liked to make the range a little bit higher because green isn't only, or the green wavelength isn't only 520 to 530. It's a lot larger, so it'd give us a little more wiggle room there. But we just tried to work around them. We found solutions to. We may not have followed all the requirements, as you guys can tell. But in the end, we got the system to work, and if we would have been able to change those requirements, we would have been meeting all of those.
Yeah, just real quick, in the discrepancy slide that I showed you guys a while back, you know, there were two there that were basically requirements that we later found out we didn't need. Like the reflectivity of the background, which we found out if we just made the software smart enough to look at the target and see the target, we don't actually need to have the background not reflect. And we actually didn't need the laser to be in that really, really narrow wavelength.
I also think over time, this just comes with engineering, like iteration through testing and requirements and just doing that over and over again is what will produce that very beneficial system. Because this is obviously, I mean, it's our first iteration design-wise, well, second iteration technically, design-wise. But if we had more time, more money, we would of course make this as the best it could be, and we would figure these things out through the requirements that we changed, through the tests that we've done. So I just think that these requirements that we would have liked to change is just a product of iteration. So.
Alfonso, I kind of have the same question for you. In a lot of these projects, the thing that always sort of hangs teams is software, and to a lesser extent, the electronic side. And you guys were able to kind of navigate through that. What were some challenges that you had? And you know, is there, if you could, you know, talk to a Capstone team coming in right now that is going to have software difficulties, do you have any advice for them before they get started?
I think just getting familiar with the programming language that you're gonna use. I think that's the main thing before starting a project like this. Some of the challenges that we had was that multi-processing, so like moving the motors, and then also like analyzing the frames that we had. So we had to do those two things at the same time. So we were learning as we went with the software. So a lot of the times we didn't know how to do certain things on Python, but we just researched and we figured it out.
Also, for advice for people coming in, get a software engineer and an electrical engineer on your team.
But kind of like a technical follow-up, I guess, software and electrical engineer kind of wise. I was skeptical internally, I don't know if I shared it with you, but I was a little bit skeptical that you guys would be able to achieve the kind of low-level control that you would need over your hardware using Python specifically, using a scripting language. Do you find that it has the capabilities that you need? Were you band-aiding your way through problems because you didn't have the level of control that you needed.
Yes, so at first we were thinking of just using the IR camera and from there measuring the distance in pixels and from there going to a distance in meters and calculating the amount of steps that we needed. But since we were not able to get like a perfect one step and then another step, we just were able to move it for a certain amount of time. We had to change kind of the algorithm for the software. So a lot of the times we were changing as we went.
So in a perfect world, in an infinite resource sort of setting, you would recommend probably something like C instead, or do you think Python's where it's at?
Yes, I think C would be good.
I just have something I really quickly want to add as to the previous question. For advice for incoming people, we did have a lot of trouble with getting those things to work, but the reason we were able to solve it is because we got a lot of the physical parts here early, and we could work on it, and our motors could not work for a month and still eventually work, right? Because we had the motors for long enough that we could continue working on them.
And to follow up,
Just to add to that, I think something that's really worth noting is, if you're going to choose Python for something like this, you have to do a lot of your own work. Rather with C, a lot of that stuff's already built, so you don't have to do it yourself. Like we had to basically make our own PWM signal, and that's why we had to use multiprocessing. So it's like we didn't have the capability with Python, so we made it ourselves, and that's kind of how it ended up going. But yeah, what were you gonna add?
I was just going to follow up with Ryan's comment to sort of lead into another question. You were talking about getting hardware in early and how important that is for your projects. Whenever you guys hire on to a major prime integrator, a feature of working in a place like that is that you have incoming inspections of hardware that you purchase, right? Can you chat with the group here about how that might have benefited you had we had the time and resource base to do that?
I think. Well, do you want it?
Well, at least for the sensor, the IR sensor, if we had that check, it would have been a little bit easier because we got the sensor in prelim, and we had it for I think two and a half months, and then we found out that wavelength wasn't able to be seen. And if we went through that inspection as soon as we got it, we'd be able to either send it back and get refunded the money to try and find a different solution, or try and make it work a little bit better. But we'd have 2.5 months to figure out a solution instead of all that time, not wasted necessarily, but not used effectively. So yeah, I think just if it would be a little bit much to add into a capstone to go through a document or a process to check everything that you get, but I think it would be very beneficial, especially in a workplace, to do that because you're saving time, you're saving any issues that you may see in the future because of some specifications that are wrong, just because you believed a company that may or may not be, not false advertising, but
Yeah, I mean, it deserves to be said. You guys did your due diligence. You went through and looked at the spec sheet, and you were convinced that it would see the wavelength that you needed, but whenever you got it in-house and did an actual physical test, experimental ground truth, no, it could not see the wavelength that you needed. So that is not something you really expect. And then I had one more question, more just because it's something I should know, and I don't know what the final number was, but what was your final cost for the project overall?
I think if we had 630-ish, it'd be 1880-ish. Around that cost. And that also helped us immensely in the end because we ended up burning a couple lasers out. So without that management reserve, we wouldn't have been able to get any more lasers. But this allowed us a lot of wiggle room in case something were to break. As well as getting that stuff early allowed us to have more wiggle room again just to buy some more stuff or or if we needed to buy a backdrop or buy another part for this targeting tripod, it allowed us to do that. Oh, okay. Of the, you want to do that? Full system or just like this?
So our big idea was this would be mounted on a satellite that you would have use this to narrow down the search and find the exact location of a piece of space debris that would be made of aluminum like our target. And then you would have a larger laser that would ablate parts of the material off of it and impart delta V and cause it to deorbit. So our idea was orbital debris remediation.
We've also found that the military may want to use this in the future. So, yes, so that could or could not be a potential use for this as well.
I just wanted to add one thing to one of the first questions that we had was that if we could do some more software to eliminate some of the noise that we had in the images. So this one, I'm not sure if you can see it, but in the monitor there, you can see the frame, and there's a lot of other white spots that are not the target. So what we tried to do at the end was that kind of the same process that we did for the visual camera, make a contour around the white spots that we had, and we have a specific size that the target is going to be. So only have that contour that's the specific size that we wanted and eliminate everything else. But that's something that we didn't get to finish, and if we had had more time, then we would have gone with